Let's go over the homework. I don't believe I did anything with the homework last time. So first homework assignment was to figure out what Python distribution you're using, have it installed. If you're depending on IT, you may still be waiting on that part. We still quite haven't gotten all the stuff set up for giving out the nthought licenses, but we have got a contract in place with nthought for, let's see, I think it's 50 users and 35 machines. The difference being, if you license nthought to yourself, then you can install it on as many computers that you personally use. Problem is that you can't install it on your beamline computer because it's used by lots of people, and then every person would have to have an nthought license. So what we've worked out is that beamline computers will be considered clusters with one node, and so we'll need a license for each beamline computer. And I think we have 30-something licenses for beamline computers and or clusters. Questions about this or IDEs or stuff like that. I haven't had much chance to play with it, but I really recommend taking a look at the Eclipse PyDev environment, and there's some really nice notes that Pete Jemian put together. I believe they're now on the PIG website, so you don't have to be inside the firewall to get access to those notes. Any questions on this? Okay. All right, real questions. All right, so the next lecture, these were the questions, and let's go through them one at a time. So what's the difference between these three statements? They all put 1 into A, but they put different type of 1. This creates an integer. This one creates a floating point number, and this one creates 1 as a string containing 1 character. You can convert them all from one type to the other, from any of those. Okay, what about this? I've defined here B as a string 3 different ways. Is there any difference between them? And the answer is no. They're exactly the same. The only difference is what the way the quotation marks that were used to define the string. If you look at what the value is inside Python, they'll be exactly the same. I put up the list of strings, and on slide 9, and I asked you where would you go for more information. And one place is to go to the Python web pages, and then you look for the standard library, and then in that you'll find types, the str definitions, and that'll eventually bring you to that section there, which documents everything. You get pretty close to there if you start at Python, start in Google and ask the obvious question. Occurs to me right now that what I should have also said is that if you typed help on any of those commands inside Python, so for example, we did this actually, maybe we didn't, let's see. So if you are inside, let's start at Python, which helps if you spell it properly, and we'll make a string variable, a equals, and then we say, first of all we can say, let's just see what happens if we type help a. Yeah, here we go. Now we've got the documentation for the string, and that shows us lots of stuff. Or we could just look up, for example, if we're interested in what does help upper do, there we go. That's a description of that. So that would have been a good way to include it on that slide. Okay, so last question was, oops, I didn't want to do that, was what are the data types for all of these various things? This one is a tuple. You can tell that because it's got parentheses around it. The list has square brackets around it. This is a string, And to be a little bit tricky, this is two strings joined with a comma. So 2 of anything joined with a comma is a tuple. The parentheses are optional. So this and then the next line with the parentheses are exactly the same thing. They're tuples. The curly brackets define a dictionary, and here we have a list containing containing 2 integers, 2 ints, and a tuple. Okay, so that's homework 1. Let's go on to homework 2. There we go. All right, so the questions were to look at an expression, to think about what happens when you make a tuple that points to some lists, to look at a comparison, and then to look at some code continuations. So let's take a look at that. This is one of those things that the answer would depend on what language you're working in. Some languages have operator precedence and some don't. Python, coming from the hand of somebody with a background in mathematics, has operator precedence. So this is the same thing as this. The multiplication gets done before the addition. So that's 6. Adding 1 gives us 7. And if you have trouble remembering, just use the parentheses. They never hurt. It's always safer. Okay, what will the value of B be after executing these 3 lines of code? So we start with A being a list containing 2, 3, and 4. We make B as a tuple containing that list twice. Then we assign the last value, 0, 1, 2, so that's the last value from being 4 to being 5 in A. So what we see is that A, after we've done these 3 things, is 2, 3, 5. That's what we expect. But what's surprising, until you get used to thinking about it, is that B is 2, 3, 5 repeated twice. Why is that? Because all that B contains is 2 references to A. So this is one of those tricky things about Python. Python doesn't copy data items unless we ask for that to happen. Question for you guys. If I wanted B to be made up of the original values of A and I don't want them to change, how would I do that? Okay. Excuse me? You could copy them element by element. That would be one way to do it. Somebody else had their hand up? Okay, same thing. Well, it turns out there's an easy way, and that is to use the addressing techniques. So, for example, let's just do that real quickly. A equals 2, 3, 4. B equals A sliced, and again, so that's a comma, A sliced. Okay, so B is that. Now I can change the last element of A to be 5, like I did last time, and B is unchanged because when I do the when I do that, actually I should show that again. When I do the when I use the slice there, I'm saying I want a copy. It's not the only way to make a copy, but that's one way to make a copy. Okay, so and I regret, but this is really one of the most confusing parts of Python. There are real advantages to the fact that Python copies references, doesn't copy the actual data item unless you want it to. Okay, so how would you do this comparison? Well, you guys are experienced folks, so you can look at this and say this less than 4 or greater than 4 means everything but equals to 4, so we can just rewrite that as not equal to 4. In terms of continuations, the idea here that I want to get across is that a continuation works very well whenever you have an open parenthesis, any kind of open symbol where it doesn't work for quotes, but anything where you have effectively you have to have an open indication and a closed indication. So this works fine. This one works fine. It doesn't have to be for a list or a tuple. Here we have an expression in parentheses. Makes doing large math expressions very nice. Just use an extra set of parentheses. But here, even though we end with a comma, you might think, well, Python is going to look for some more stuff. It doesn't. Even if you ended an expression with a plus sign, it's not going to work because it only pays attention to things like parentheses and the different types of brackets. This one here? This one here, A would be 1 and 2, would be a tuple containing 1 and 2, and then it will give you an error message on the next line for 3 because there's nothing there. If I'd made the unfortunate mistake of putting 3 right at the lined up with A, then it wouldn't have a syntax problem because 3 on a line by itself is just fine. Yes, Pete. The error message is only because of indentation. That's correct. It's only because of the indentation. But usually you wouldn't be so unlucky. Okay. All right. Last one is I gave you a homework assignment to compute n factorial 2 different ways. The first way was using a while loop. I remind you what n factorial is, and I actually made a minor. It's not a real. It's an inconsequential mistake. I had meant to go from n to 2, and this turns out to go through to 1. But I just set my variable n here so that it's defined. I set up the product to be that variable. By the way, does it make a copy here, or does it just reference n? No, it references n. So it's gonna at the moment n both n and product reference 5. However, a little while I'm going to change n, and that's going to reference a new constant. So product doesn't. So it doesn't. When I change n down here, I don't change product. Excuse me. So, okay, is n greater than 1? The answer is yes, because it's 5. So I subtract 1 from n. I multiply product by my new value of n. So now, if I started with 5 at this point, n is 4, and product is 5 times 4, and it's reached the end of my loop, so it goes back to the beginning of the loop, and now n is 4, subtracts 1, multiplies by 3. And it will keep doing that until n gets to be 1, at which point it multiplies by 1, it comes back here, n is no longer greater than 1, so it doesn't do anything else. And it drops out, and if I look at what the value of product is, I see it's the same thing as 5 times 4 times 3 times 2 times 1, as it turns out. So that's how you do this with a while loop. You can do this even more simply with a for loop and the range command. You just have to remember that you need to do a range of n plus 1 to get the values 2, 3, 4, 5, ... n. If you did this just up to n, you would stop at n minus 1. So this will generate, so I start by setting the product now to 1, and this will generate the integers from 2 to 5, and then I just loop over this, multiplying product each time. So again, I get the same result. Okay, questions? Okay, so let's actually start doing something new. 5. Okay. File I/O. All right. For you guys who've done programming, I don't have to explain why you might need to access files, just how to do it. When you work with files, you do the normal sorts of stuff. You open them. For those of you who've done programming, console programming in Unix, you know what standard I/O is. We'll talk about how to write to a file, closing the file, reading from the file, and a little bit about formatting text. Formatting text is one of the gotchas because it's something that's changing between Python 3 and 4. Okay, so opening a file works just like most other languages these days. You call open, you give it a file name, you tell it what mode you want to open the file in, and it creates some kind of file pointer, file object. Okay, file name is a string, or it could be a variable pointing to a string. The mode can be a number of things, but most commonly is either R for read, in which case you're not going to change the file, W for write, in which case you're going to change the file, A for append, which means that you're going to add to the end of the file. In R, the file better exist because you can't read from a file that doesn't exist. If it's W, the file can exist or not. If the file already exists, it's going to just write over it. And for append, if the file doesn't exist, it'll create it for you. If there's more things you can do here, and I refer you to the web page. What's a little different about Python is that once you've created this file object, just like with a string, it has lots of methods. It has lots of routines associated with it, like these here, and they're all described below, and we'll see how those work. So before I do that, though, I should mention that there are some file objects already created for you. We'll talk about a little bit more about how you get to stuff in the sys module when we talk about modules, but you can get information from the terminal if you're talking to a terminal window or a DOS box, or send it to the terminal or DOS box. These things aren't terribly useful necessarily if you're working in a GUI type environment where those things may not be defined. Also, error output can go to standard error. These things already exist for you. You don't need to use open to get to them if you want to use them. Okay, so how do you write to a file? First thing, you've got to open it. So here I'm opening a file. I'm opening it in append mode. I'm writing some character string to it. And then, unlike printing, which we talked about earlier, when you write to a file, it does not start a new line. So if you want to write a file one character at a time, you can do that. Was that a hand up there? Question? No. Okay. So when you want a new line, you need to put it in specifically. So the next thing is, what about when you're done with the file? The best thing to do is to close it. This routine here will close the file for you eventually, one hopes sometime when Python gets around to doing its cleanup, because we've created an object, we've written to it, and then we've returned. That object is no longer defined anywhere, so Python can say, okay, I'm done with this, I can clean it up and close the file and get rid of it. But the fact is, it may not. And it turns out you can even make this routine even a little simpler by doing an open, doing a write, in this case, and then just going away, because I don't have to actually store the name of the pointer, the file object, anywhere. But having said all of these things, these are not recommended ways to write to files, because there's no guarantee the file will get closed right away. So I recommend sticking in the close all the time, and if you really want to do this, there is a new statement in Python called with that forces the garbage collection right away, but I just recommend not doing it. Okay, so let's talk about reading from a file. Yes? Go on. Okay, the question is, what happens if you have a file open? The answer is, depends on what kind of program you're writing. If you're writing a program that's going to open a file and then go do something, open an input file, read from that input file, the input file stays open, and then you go off and do something else, you open an output file, and then you finish. No problem. Doesn't matter. The problem comes in when you write a program that runs for a month and it keeps opening files and doesn't close them. Because then you basically got a memory leak. So you're allocating space for this file, and you're never getting rid of it. So you know, rather than tell you to use two different modes of programming when you're doing something that's going to run forever versus something that's going to run occasionally and for a short period. That's why I just emphasize it. Yes, you're right. Under most circumstances, it doesn't matter. Okay, your question. If you don't close the file, can you delete it? That's going to depend on the operating system. As far as I know, if Python still has the file open, different operating systems will handle it different ways. You had a question? Mm-hmm. That's also potentially true. Actually, what's even potentially worse is if you don't close the file, the information, the last bits of information that you wanted to put into that file are sitting in a buffer, and unless you specifically flush it, may never get written out. And if the computer crashes before the before you close it or flush it, then it will never get written. So again, it's just good programming practice to close a file when you're not using it. Reading from a file turns out is exceedingly easy. You open your file. You open your file, and if you want to read over the whole thing, you can just iterate over the file. So you put a for loop, and each line of the file successively will get stuck into the variable line. And that includes the carriage return on the end of the line. So I've intentionally pulled that off so that I don't have two carriage returns here. Yes? Yes. The turn line has no meaning. I could have spelled that any way I wanted to, or I could have made it just L, or I could have made it. It's right. It's not. Yes. It's not a. This is not a line. Here is not a keyword. Yeah. So maybe it would have been more clear if I'd made the example something other than line. But yeah, I tend to use variables that have obvious meanings. So this routine will now read through all of the contents of this file and keep printing it all out. Let's see. This is actually a newer syntax in Python. Previously, to do this, you had to call a routine called fp.xreadlines. And what this is doing is it's actually just buffering the information and it's pulling in it as you need it. We'll see there are other ways to read files. This is probably the most efficient way. And you might see this in older code, which is why I mention it. But this is the modern replacement for that, and it works, and it's very clean. But you might want to do other ways of reading a file. So, and by the way, you don't even have to do this in two steps. Just simply when I open, that returns a file object. So I can just put my open statement right in to the for loop. But if I do that, I can't do the close. So again, I don't really recommend this. But it's very clean. It's very simple. And it's very obvious what it's doing once you get used to the syntax. Let's see. So what are the ways you can read a file? What if you want to just get one line? I'm going to a certain place. I want to read a line. I want to do something. I don't want to read any further. Well, fp.read will return. Well, actually, that's not what we probably want to do. fp.read reads in everything. It gives us one big long string that contains every character in the file. Or if I want to, I can tell it to only read a certain number of bytes, and it will stop for that number of bytes. That's the syntax. You're not going to want to do this very often. There are occasions where you might want to, but in general, you're not going to want to do this, certainly not for ASCII files. Read line will give us one line out of the file. Read lines, with that extra S, reads every line of the file, sticking it into, I forget if it's a list or a tuple. It's a list. Gives us a list where each element in the list is every line in the file. You might want to do that with a smaller size file if you're going to do multiple processes around the file, where first thing you want to do is just look and see what's something in there, and then based on something you've seen in the file, go back and process it again. You're not going to want to do that for a very large file. Let's see. What about if you, as in science, we want to spend a lot of time dealing with files that have stuff in columns of some fashion, either separated by commas or spaces or tabs or something like that. It's not that hard to parse that stuff on your own, but Python has that work already done for us in a package called CSV. So if you want to do that, you might want to take a look at the package. If you're going to take that column or information and you're going to do, for example, linear algebra on it, you might want to put it directly into a NumPy array, and NumPy has a routine fairly sophisticated for reading, again, these comma-separated variable type files. So again, those are references if you get into that point where you want to do those things. All right. Yes, question? Yeah, those are, let's see if I can show you. You can absolutely do that. Seek will position the file where you want it to be, and tell will tell you where you are in the file. So you can absolutely do those things. Okay. So formatting. You'll see this kind of code frequently in Python expressions, and what this is doing is these %ds and %s values are doing formatting for us. So it takes this string, and then it sees the %, which is the format operation, and then it either sees a single value or a list of or a tuple of values, and it will put those values into the expression. So here we're looking for 3 different values. The first 2 better be decimal numbers, and the third one can be a string. And what it will do is it will stick in 1, 2, and 3, and it doesn't treat the the integer. It just converts that to a string representation, which is 3. So that's what this statement here produces, that in string. Python 3, they decided they don't like this expression. They depreciated it. Doesn't mean it's gone. It's still there, but they're discouraging its use. And someday, and I doubt it'll be someday soon, but someday it will go away. So I'm going to suggest you don't use this. The Python 3 way to do the same thing is this, and that will work in Python 2.6 and later. But unfortunately, we have Python 2.5 on our beamlines, so we can't use this one yet if you're working on the beamline. So what do? Well, turns out that you can just avoid it for most things. If you really want very precise control and you want 3.333 to show up with exactly 3 decimal places and no more and no less, then you'll need to use one of those 2 format operations. But in general, we just want to see what we've got. So we can take, we can do string operations in a very simple way. So that same string could be generated by saying, stick in a string representation of 1. So let's concatenate a bunch of character strings, one of which is the string representation of 1, second one is a string representation of 2, third one is a string representation of 3. And I should explain that what that does is virtually every Python object has two different things that will convert that Python object to some kind of string, one of which is str and the other one is repr, short for representation. And if we look at the string value associated with this float 1.1, we see it's nicely formatted. If we look at its representation, it shows it to us in all the digits that Python is keeping behind the scenes for us. So, rule of thumb, if you want to show a value to a user, use str. If you're using debugging, you may want to see more information, so repr might be more appropriate for an error statement. Okay, and if you do this, first of all, it's fairly simple, and second of all, you don't have to worry about your code changing. This will work in Python 2, it'll work in Python 3. All right, so a little bit of homework. Write a short script that writes a file. My suggestion is put your name, office location, and phone extension. If you consider that personal information you don't want to deal with, then you can put anything else you want. But then write another short script that reads this and prints it out like that. Okay, give yourself a little bit of chance to do something simple that reads and writes a file. Okay. More questions on file handling before I move on? Yeah. Right. Right. When we iterate over a file like here. FP is this is a little bit higher level coding than I want to get into at this stage, but let me answer your question. What FP is actually something called an iterator, and you can write these yourself. What an iterator is a function that returns a number of different values, one of which is the next value in a sequence, or it can return I'm done with the sequence. So what's going on here is that FP is pulling in from the disk each line of the file as you need it, and it never keeps more in memory than it needs to. Mind you, it does lots of buffering because that speeds up the computer, but so that's what it's actually doing is it's doing something called an iterator, and that's really the most efficient way that it can do these things. But I didn't want to explain that because it's a little advanced. More questions? Okay, so let's get rid of this one and go on to 6. There's 6. Okay, I got a compliment from somebody on this one because error handling is often considered something that's pretty advanced, and I think it's one of the parts of basic Python, and I really encourage you to use it pretty much from the beginning. And certainly when we get next week to doing epics handling programming, we're going to need it. So we'll talk about what kinds of errors you can have. We'll talk about what Python does when it gets an error. We'll talk about how we can have Python do different things when it gets an error by using a statement called try. We'll also talk about how we invoke errors. And that's one place where I really encourage you to think about doing that, to do that, and how you would define your own classes of errors if you want to. And then finally, a little bit about programming strategy using exceptions. Okay, so I'm going to say, first thing I should say is that I'm going to use the terms exceptions and errors, perhaps, unfortunately, somewhat interchangeably, but they are different things. First thing is, the most common kind of error you're going to have is a syntax error. This code here contains a syntax error, and I intentionally made it a little bit inobvious, and actually Microsoft PowerPoint helped me by putting it in there for me before I did anything else. That F is not supposed to be capitalized. The keyword for in a loop consists of 3 lowercase letters. So Python is going to object to this line before it starts running any code, and it's going to tell me that's a syntax error. We can't catch those usually because they are going to pop up immediately. The errors that we're going to try to worry about are what happens when we're actually running the code. These are called runtime errors. And we've seen in previous slides a bunch of different runtime errors. So I went back and I pulled them out. So these are the errors we've seen. When I asked for an integer representation or convert complex number to an integer, I got a type error because it can't do that. When I try to change a value inside a tuple, again, I got a type error. When I tried to take a list with 3 elements and put it into 4 values, I got a value error. When I tried to assign a list element that doesn't exist, I get an index error. When I try to reference true, a string here, but that's not defined, true is supposed to be capitalized, I get a name error. And each of these errors represents an exception type. This is why I have a tendency to mix up exception and error, because for my mind they're equivalent. So you can think of type error, value error, all these things as types of exceptions. So what happens when I'm doing these sorts of things and I'm running a Python script and it comes to one of those errors? Well, the Python script interpreter stops. So if I've done a simple Python script and I invoke it, it runs up to the point where it hits one of those errors and it stops. As it turns out, when you're running Python from a graphical user interface, Python runs very differently. What it will do is it'll run through a certain amount of code, create the graphical user interface, get started, and if at any point in that point it comes to one of these errors, it'll just stop. But from that point on, what Python is going to do is it's going to respond to what are called events. An event could be pushing a button. An event could be a timer going off. An event could be something external to your program that invokes a routine. In any of those cases, if you hit one of those errors, it will run through this routine up to the point where it hits the exception, up to the point where it's the error, and then it'll stop running that routine, but it goes back to waiting for more events. So it's a little different. Those default things are not necessarily what you want to happen. It might be. If you're running a simple script, you're typing, you're clicking on a program, you want it to say, good morning, and if it hits an error, it's fine that it just comes back and aborts. That might be fine. But if you're doing something more sophisticated where you're writing for a user, you probably want to tell them that something went wrong and give them a hint about what they need to do next. And certainly, if you're running something that's going to work, that's going to run a beamline unattended or something like that, you really don't want it to just go belly up. So how do you deal with that? Well, Python gives us something called try, and then a way to work with to see what happens. So here's an example taken from my own code. When the main routine that collects data from mail-in samples on 11BM is called run 11BM mail-in samples _inner. And the sample table and the run list give it the information it needs to know as to how it's going to actually collect the data. And you'll see that this has got a try statement in front of it. And if this throws an exception, an error, an unhandled error happens inside this routine, rather than just having the data collection stop running, it comes up with an error message, and we'll talk about what this stuff does later. It sticks that error message into a log file, and it sends Lynn a message on his cell phone telling him that the instrument stopped. Me too. So that he knows that the data collection has failed, and then can and knows that something's wrong. So it'll turn out that there are lots of errors that we look for inside this routine and we handle without stopping. But this is what happens when we have an unexpected error that we don't know how to deal with. Okay. So the full syntax, if you want to use all of it, for try is to say try, then you indent and you have one or more statements inside the try block. If any of those statements triggers an exception, you then have exception and a exception class, a condition, and an optional error message variable that gets set with the error message. And so if an exception occurs in here and it matches that, then these statements will be run. If not, if the condition matches this, then these statements will be run. If the statements execute without causing any exception at all, then else gets run. And if any exception happens, even if it's not matched, the finally statements get run. So as an example of something that you might want to do is if it's really, really important that you close a file, then you would put your file handling statements inside here and the finally would close the file. Because then you can guarantee the finally always gets done. These things are optional. And one more thing I should mention is that if you say except followed by exception, or even except followed by nothing, just the colon, that will catch all exceptions. So here's an example of something. I won't explain exactly what this does. It's something called a list comprehension, and it takes a for loop and it compresses it down to one line. And I only did it this way because I wanted to keep the slide short. But the basic idea is that this will throw an error if I look for a value in a dictionary that doesn't exist. So it's going to run through this, and if I hit that particular error, I'm going to get a key error, and it will do this. And this is the way that I would recommend you write your code. If I just stuck except here, then there's a possibility that there's something else that's going to go wrong in these statements that I didn't expect, and I might never know about it. I'll never know about it because this is going to run, it's going to do something, and it's going to proceed on, and then I'm going to hit some later error in my code because something that I wanted to do didn't get done. So I don't recommend doing these things if you're going to continue your execution. Trap only the errors that you expect if you're going to continue. Because what's worse than getting an error message and having your program stop? It's getting no error message when you wish your program would have stopped. Okay. Moving on a little bit. Actually, one point I want to emphasize is that try blocks can be nested. And in this example, the try blocks are nested by the fact that there are lots of try blocks inside this routine. The try blocks that are inside this routine are the ones that handle errors that I expect and I know how to deal with. So there's nothing wrong with nesting try blocks, and it's a really good idea to have an outermost try block to act on the errors that you don't expect. Yeah, Dennis. Okay. The answer is that it may or may not, which is why you don't really worry, why you don't use try as an attempt to deal with syntax errors. Yeah. Okay. Well, the answer is that there's two passes. There is a first pass that Python will do when you just give it the file, and it goes through and it parses out what the file is supposed to do. And it will catch a certain level of syntax errors at that point as it looks at the file initially. But other things are not clear syntax errors. So for example, that case where I had the list and I had the wrong indentation, it will catch that immediately because it gets that when it's just trying to interpret the code. It can't figure out what the loop structure is until it's done that. There's other types of syntax errors that it won't necessarily catch until it actually tries to run your code. So I don't know if this is true or not, but if you had accidentally typed plus twice in a row, it might not be able to, it probably can't interpret that as an error until it actually tries to run that code, because plus is what plus does is defined in the context of what it's operating on. You'll find that out. I mean, you can't try, under those circumstances, you will throw an exception, and you could trap the syntax error. You can trap it, but that's one of those things that you would trap by going belly up, most likely. Okay, so having said that, one thing that I think is really valuable to do is to create your own errors. And there's a real simple reason why you want to do this, but let's just see how you do it. Here, what I'm doing is if I get an error, a key error, I'm going to turn around, I'm going to log it, and I'm going to throw my own error. Okay? That's one way you might do it. You might do it just on an if statement. If something happens that I don't want, raise an exception. Okay? So let's see. How do you define your own? Okay, so I'm sorry, I skipped over this slide by accident. So here's how you throw an exception. You say raise. You give it an exception name. The exception name could be just exception because that's a valid type. You can use value error, syntax error, all those other various things that are already defined. You can optionally include an error message. But very often you may want to define your own class of exceptions, and you do that like this. You just follow this boilerplate right here. Just copy it exactly. And my error, you'd change to be what you want the error to be named. You'd put your own value here, and when the exception occurs, you get some sort of value associated with it, and this code here converts that to a string and sticks it into my error message. So if I say raise my error, comma 42, then this is and so I get this, I trap it with this here, and then I print it out. So what this does is it prints out my error message, and there's the 42 coming up because I passed the value there. Okay, so that's how you create your own exception class. So all you need to do is to change this, and to change the name of it, and to change what you want it to return. Okay, so strategies. Why use exception rather than? I mean, you can always, if you have a routine, it can always return when it hits an error. Why raise an exception? Well, the answer is if you think about when you're running a bunch of routines, you may go through a whole bunch of routines and you end up somewhere, 5 levels deep. Or depending on how you call that same routine, you might be 3 levels deep or 7 levels deep. When you return, it just brings you up to the calling routine. So you've got to somehow recognize that you've returned from an error and you've got to do something different once you've returned. Instead, you can think of raising an exception as get me the hell out of there. Okay? When you raise an exception, it doesn't matter how deep you are in your call stack. It will bring you right up to the level of the immediate error handler. So it gives you an easy way to say, sort of the old kind of Fortran go-to. I'm somewhere in my code I've hit something that I don't want to, that needs to be dealt with. Bring me out to the level of the error handler. And it doesn't matter how I got there. Just bring me out to that error handler. Okay. I've said this stuff already about nesting errors, nesting error handlers. I have try blocks for things that I expect. I write code these days so that I will get exceptions that I expect when things will happen that that I want to deal with. So then I use a try block to catch those. But if errors happen elsewhere in my code, as the example I gave you, I may want to do different things. Okay. So let's see. And you may be able to do that by just having one try block, which has multiple except my value error do this, except key error do this, except exception everything else do this. But more likely you're going to probably want to nest them. Okay. Last and probably most important thing to mention about what happens when you get an error. So here's a very simple script. It starts by defining a routine called junk. Anytime I run it, it's going to generate a divide by zero error. Then I have another routine that calls this, and then finally I call that routine. When I run this thing without doing any try blocks, I get this stuff printed out, this traceback. And we can read this traceback in reverse order. The last thing it tells us is the error that we hit. The thing before it, it tells us what line that error occurred. It was line 2 in function, line 2 in my file, line 2 in this file, in function junk, I did this. Then it tells me what I did to get to there. Well, I was in line 5, calling junk, and this was executed when I did call junk at that line from line 7. That's called a traceback. And that's something that's very useful in figuring out where things went wrong. You don't want to throw that away. So how do you get that to stick in your own, to do what you want to with? Well, the answer is that there's a library, or actually a module called traceback, and this is some code that you can use to get that. So I've opened so if I get an exception, I open the file, I write out an error message for myself saying that calls a time, that gives me a timestamp, and then I print that traceback information into my file, and then I close my file. Okay, so this is just sample example code on how to set up error logging, so that when I run my routine now, it will take the traceback information and put it into an error file. So that's what's happened here. Is it ran? It didn't produce any errors that are obvious, because I could have changed that if I'd told it to print something here. But the error message got diverted to a log file. Okay, so here's some quick homework. Write a short script that divides 10 by the elements in this list. 10.0 divided by 10 is not a problem. 10.0 divided by 5 integer is not a problem. 10.0 divided by 0 is a problem, and it doesn't matter whether it's dividing by 0 integer or 0 string. Both of those are going to produce errors. So if there's no error, print out the result. If there is a divide by 0 error, print out divide by 0. If you divide by a string, print out something different. You might write a more explicit error message than that, but that's what you need to do. Okay, so that's how you handle errors. And let's go on to 7. And it looks like I've got to load up another one, but all right. Okay, so 7, let's talk about the modules that are in Python that are available for you to use, and the functions that are already there. there's lots of stuff that is built into the language directly. There's even more stuff that you can ask for the modules. And there's lots of these modules are built into the language, but there are other ones that are available effectively from third parties. Finally, how do you get the modules if you want them and they're not, and how does that work? Okay, so let's talk first about the built-in routines that are part of, well, first of all, just simply, Python is awfully powerful. There's lots and lots of stuff that Python can do, so to speak, out of the box. But when you start adding in the modules that other people support to help Python do stuff, like, for example, talk to epics, it becomes even more fully featured. But there's starting with the stuff that's built into the language from the beginning that you just get automatically. There are about 80 built-in routines. I've made a list here of some of the things that I think are most commonly used. It's well worth your time looking at the web page and looking at all of them. So to pick out a couple of these, some of these are obvious. Absolute value, it's absolute value. Any will look at a list of things and tell you if any one of those is true. So it'll OR the list. All is gives you will AND the list. It will be true only if everything in it is true. I've shown you direct to look at the dir to look at and help to look at information about an object as well as its type. Min and max are obvious. Open we've talked about. POW is for power. Both of these work, by the way. Raw input is only going to be useful if you're going to work from in a DOS box or command or terminal emulator. Rounding is obvious. Sorting is obvious. Zip we talked about earlier, so I won't talk about that one again. In addition, there are something on the order of 200 modules that come with Python, regardless of where you get it. Okay, if you just go to the Python webpage, download vanilla flavored Python, you'll get something like 200 modules. And of those modules, this is a handful that you might most likely use. It's got a mathematics library. That's where sine and cosine live, exponentiation. For manipulating paths, manipulating directory names, system access, file globbing, which means doing wildcards for file lists, operating, regular expressions. Pickle is a nice way of taking a Python object, converting it to something that you can stick in a file and read back later. You can access the time. There's also the datetime module for more complicated things. Emailing, it's got a debugger. Subprocess allows you to launch other actions. So, for example, you're running along, you then want to go do something that requires a system level command. You can do that with subprocess. You're running along, you want to go launch some task that's going to take a week to complete. You can go do that as well and then continue running or wait for it to finish. PyDoc is really sort of a standalone program we'll talk about later for doing, but it is invocable from inside Python. And if you want to see how fast a snippet of code works, you can use timeit to do that. But that's not all. There's lots more up there. Okay, how do you access these things? Let's take a quick example. In sys, if you look up documentation on sys, you'll see there's a bunch of stuff in there, one of which is sys.platform. That tells you the name of the type of computer you're running. Another thing is in there is exit. That exits the routine that you're running. And then finally it defines something called the path. And if you look at path, you'll see that it is a list. So since sys.path is a list, append is there because it's just a list variable. When you do this import sys in your code, the first thing that happens the first time you do it is it will actually run the Python code that's inside that sys module. If you call it again within the same program, whether it's in the same file or a different file, it doesn't do it again. It just simply looks up, hey, I did this already, I don't need to read it again. that's sometimes a nuisance, because sometimes when you're debugging a program, you want to say, don't work with the old version of the package that I want. Go read it again. And you can do that. That's done with the reload command, which forces it to reload it. But the thing to know is that it's going to do this, and it's going to do it once. And you'll notice that everything that I've accessed from sys is prefixed by sys dot, so I can keep track of it. So if I have a variable called platform in my code, this is a new one. It's not going to be touched by dealing with anything in sys. So the namespaces are separate. One warning is that I showed you this os.path. That's a hierarchical package. You can import OS, and in this case you'll get everything that's in os.path. But that was an option that's up to the developer of the package, because in other cases, in order to get the sub-package, you need to load it specifically. So the documentation for the package will tell you that. But just understand that in some cases importing OS will be enough to get os.path, but importing SciPy is not going to get you scipy.special, where the Bessel functions live. And there's a good reason for this. The reason is that SciPy takes a lot to load, and it doesn't give you everything unless you're going to, by default, you have to ask for it. Okay. There are other ways to use the import statement. Sys was pretty short, but if I'm importing package with a long name, that does sound sort of Mighty Python-ish. I don't want to type package with a long name dot function. I can abbreviate it off at the top by saying import it as this, and now I've defined an alias for it. I could do that a different way as well, by just saying import it and then define a new variable. This variable points to that. The difference is that if I do this, I define the package two ways, so I can use either name. And it's pretty common to do this. You'll see in a lot of examples, people will import NumPy as NP, because it's just a lot easier to type NP than it is to type NumPy every time you're using it. You can also do this. You can import a from a package, import specific routines. When you do this, you pull in these things without the prefix. That is not the best idea, because now, for example, this version of platform will conflict with a version of the variable platform that's or routine or whatever else that's in my code with that same name. Also, it makes it tough for the user to understand where platform came from if somebody's reading your code, or when you're reading your code after having not looked at it for 6 months. So let's see. So and this statement is really a bad one to use, but I pointed out because you'll see it. From sys import star, pull in everything into my routine without prefixes. That's a potential recipe for a disaster, because now you have a potential for conflict between a name that you never realized was defined or gets defined in a later version of the package. So you'll see this in examples where people are trying to show you things that are things that are defined. You know, for example, plotting package. We'll just do a short example using this first. But I really recommend you don't do this in your code. Okay, so there are lots and lots of other modules that are defined for Python. Something like 14,000. Not all of them work. Not all of them have been updated in perhaps even a decade, but they're there, and they're sometimes very useful as a starting place, even if they're old. If somebody else has done it first, you may want to look at their code first before you do it yourself. Some of these things are really really sophisticated. We'll be talking about these guys later. When you grab one of these packages, you may install it into Python on your system. You may install it somewhere for your own use, though. So how do you deal with that? Okay. So modules are looked for in a path. So if you ask for sys, it goes through the Python will go through the path and look for the first module named sys that it finds in the path. So if you're adding your own modules, or you're adding somebody else's own modules, and they're not in one of the standard places where Python's going to look, you're going to need to append that location to your path. Occasionally, you might even want to put your entry into the path right at the beginning, which you can do by this insert 0, so that it'll find your package first. But if you do that, and you write your own package named sys, you're asking for problems, because then any code that references sys is going to use your sys rather than the one that's built into Python. Might be what you want, but it probably isn't. Okay, so here's some quick homework. Look for the Python standard definitions to see if you can find a function that converts an integer to hexadecimal representation. Find a module that handles dates and times and prints out the current date and time. And I give you some hints there. Okay, so let me go on to the last presentation I want to give to you guys, which is there. Okay, and so much for using other people's code. How do you write your own? Okay, how are you going to write your own functions? So we'll talk about defining functions. This is going to be a simplistic guide. There's more to this stuff than I'm going to tell you, but I'll tell you enough to get yourself started. And, so you've seen an example of this already, but I didn't put too much into it. You define a function by saying def. This would be out at the margin if I'm not indented for some other reason. Then I give it a name of a function. Then I give it information about the parameters that are going to be called in the function. Then I've got a colon. The colon is important. Then I got a bunch of statements, optionally ending with return, although I can have return somewhere in the middle too if I want. And then I end the indent. And the indent tells Python where the function ends. And as soon as you've done that, the Python has that function ready for you to use. So you can just call it. What happens if I don't have a return statement? My function just ends without a return. Same thing that happens if I have a return without a value specified. The return value is none. So you can always do this. You can always say var equals a function. But if the function doesn't return anything, that var will get the value of none. Okay. So let's take a look at defining a function. I've taken the factorial code we did before, and I've put it into a function here, and so I call factorial. My argument is n. And so I do exactly what I did before. And the last thing I do is return the product. So the function is, the first line is indented. All the relator statements are relative to that. So I have to indent this twice to indicate it's part of the for loop. When I call the function, if I call factorial paren 3, 3 gets assigned to n. And I get back a value of 6. It returns 6. I could also say, f equals factorial 3, and then it would go into f. That's all pretty straightforward. Talk a little bit about what happens with variables. The variable prod here is local to factorial. Okay, so if I define prod first, call factorial, and look at the value, it hasn't changed. If I delete it, it doesn't define it for me at the global level. Okay. However, it doesn't always work that way. I've taken this factorial and I have now not provided n as an argument. It takes no arguments, but I'm still using n here. N is being used before it's defined. When a variable is used inside a function before it's defined, Python will look at it successively at every outer layer so that it assumes this must be a global variable. And so if I call factorial now, it tells me, hey, n isn't defined, I can't do anything. But if I define n and then call factorial, it uses it. Okay? This is just the way it works. I think that it, there are, from a computer science perspective, this is probably not the right way to go. You would insist on more modularization. From a user friendliness perspective, this is the right way to go. It means that you can use code and you don't necessarily have to pass every single thing you want to get into it. Okay, so what if I want to define a variable and I want it to be accessible externally? This global statement says that prod is now a global variable, so I can define it as 0, call my factorial, and now prod has been overwritten by the variable that was used inside my function. Okay, in general, global variables are not a good thing to use. They create messy code. Wherever possible, it's much cleaner to return something and use a return variable. But there are going to be times when you may find that you need something like that. If you find yourself using this, it's probably giving you a hint that you should be using a class to define stuff that comes later. Okay. Okay. Naming. Function name can be anything you want it to be. It's restricted by the same rules as variables. Can't start with a number. Case sensitive. Length is limited by what you're willing to type and your computer's memory, and that's about it. If you look at that value, it's a pointer to a function. You can copy that to something else. So here I've put my function pointer into another variable, and I can call, once I've done that, I can call that as well. There's nothing magic about functions. They're just variables that point to something that does something, and the way you're telling Python you want to use it is those parentheses afterwards. So that comes out very valuable because you can pass functions. You can put functions inside dictionaries, things like references to functions inside dictionaries, things like that. Arguments, the parameters we pass. The parameters are here I've got a function defined with 3 parameters, and there I return the variables. So here this calls that. I can also specify the parameters by keyword. So instead of saying them, specifying them in the order 1, 2, and 3, P1, P2, P3, if I specify them by keyword, I can put them in any order I want to. I can mix that. The first one is going to be P1, but I have to pass the right number. I've defined that they're going to be 3, there better be 3. Okay, here, whether I do it by keyword or not, 2 isn't enough. Okay, I can define default values for parameters. So here I've added P2 equals 2 and P3 equals 3. Now I've defined a function that will take 1, 2, or 3, but not 4 and not 0 parameters. So if I use it as I did before, I get exactly the same result, sticking 1 here, 2 here, 3 here. But if I only call it with 1 argument, I get the defaults for these guys. So this now works. It didn't work before because it only specified 2 of the parameters, but now P2 is going to default to its value of 2. It turns out you can do even more sophisticated things. You can have you can pass arbitrary parameters. You can pass an arbitrary number of parameters, but we'll deal with that later. Okay. What happens if you modify a parameter? So here I've got a one-line function, and all it does is redefine the variable that's been assigned to the parameter. You might think that if I set b to be a value and then I call this, b is going to come back being 1. But it isn't. And you can understand why that's the case, because it's created a new variable a. My new variable a initially points to this object 10, but when I say a equals 1, then I point a to a new object, so it never changes b. But just as before, when we do pass pointers to objects and we change the object, then we can change it. So here is a new function which is going to change the first value in a to be 1. So if I pass this list to the function, it does change the first element. And somebody asked what would happen if I did that with a dictionary. If I did that with a dictionary, it would either redefine or add the key 0. But I can't do this on a tuple because tuples are immutable, so it won't let me change that. Okay, so we didn't really talk too much about return, but I told you it's optional. If you don't have a return statement, the value none is returned. Likewise, if you use return without a value, it returns the value none. You cannot return more than one thing, but you can return a tuple. This looks like it's returning more than one thing. It's not. This is making a tuple out of these three values, whatever they are, and returning that tuple. Okay? And one thing that's very common is if you know that you have a routine that's going to always return three values, you might say a comma b comma c equals the value of the function, because it's making a tuple and you're going to take that tuple and you're going to map it on to three variables. So it looks like Python is allowing you to return more than one thing, but in reality what it's doing here is it's making a tuple. Okay, so I'm getting close to the end of the time I've got. A few comments on good programming practices. First thing is, write functions. Write lots of functions. Don't make your functions do too much. Make your functions do simple things. Why? Well, one reason is that it's going to help you when you document that function to say this function does the following thing, and when it's done it's going to return this, and this is what it expects as input. It also is going to help you test it. When you write a function, how do you know it's doing the right thing? Test it in as many ways as you can figure out. We'll talk later about how to set up unit tests, but if you're writing some sort of calculation subroutine, one of the first things to try to do is to figure out what is this calculation subroutine, what kinds of numbers is it valid on for. Let's try to test it out on as many different conditions as we can, and preferably generate that some other way, from some other program, from a math table, something like that, so that you really know that it's doing what it should do. And I'll mention that some of the most impressive programmers I've ever seen will sit down, they'll write out documentation for what the function they want to do will do. They will gather the test input for how they're going to for what the function is supposed to calculate, and then they write the code. Then when they've tested it, they really have a pretty good idea they've written what they wanted to write. I won't say I always do that. I will say I do it occasionally. Okay, so a little bit of homework. Write a function that that accepts 2, 3, or 4 arguments, but not 1 or more, and gives you the product of those. Write 2, 3, or 4 arguments and returns a tuple of length 2, where the first item is the product and the second item is the sum. Okay. So just to give you some practice writing some short functions.